Hello my dear students, today we are going to study the topic General Register Organization in subject Computer Organization and Architecture. My name is Himanshi Chaudhary. I am from Department Computer Science and Engineering, Kite Group of Institution. Let's get started. So first of all, we will see that what are the prerequisites. It means what you must know before going through this topic. So you must have seen the video for registers and register transfer and memory transfer. Then you must know about what is multiplexer, because that we will be needing in studying general register organization. So let's see what is multiplexer. Multiplexer is a combinational circuit that has maximum 2 to the power n data inputs, n selection lines and single output line. It means that we will be having some inputs that count will be 2 to the power n. If the count is 2 to the power n, then n will be the number of select lines and the output will be 1, only single output. These are some of the examples of multiplexer. 2 into 1 multiplexer, it means it is 2 to the power 1 inputs and 1 output, and if 2 to the power 1 is the number of input, then 1 is the number of select lines. 4 into 1 multiplexer, in this 4 is to the power 2, so there will be 2 number of select lines and 1 will always be the output. Then 8 into 1 multiplexer, 8 is 2 to the power 3, then 3 will be the number of select lines and 1 will be the output. It is bold because we will be using this in our topic. Next is 16 is to 1 multiplexer. It means there will be 16 number of inputs and it's 2 to the power 4. So there will be 4 select lines, and as always in multiplexer there will be 1 single output. Let's see the block diagram of multiplexer. So this block diagram is showing that there will be number of inputs. This will be 2 to the power n data inputs, and there will be select lines inside, on the basis of which one of the input is selected and the output is given. Okay, so here it means that the select lines will select which input will be the output. This is the truth table for this multiplexer. Let's take the example for 4 into 1. If it is 4 into 1, there will be 2 select lines. If there are 2 inputs, then the possible binary combinations will be 0, 0, 0, 1, 1, 0 and 1, 1. These will be the inputs A, B, C, D. If A is input, then on the basis of select line, A will be the output. If 0, 1 is the input on select lines, then B will be the output. If 1, 0 is the input, then C is the output. If 1, 1 is the input, then D is the output. Let's take the example of 8 into 1 multiplexer. Here 8 will be the count of input and it will be power of 2 to the power 3. So the number of select lines will be 3 and output will always be 1. So on the basis of these 3 inputs, on the basis of the possible combination of these 3 binary select lines, one of the input from these 8, that one will be output. This is the block diagram for the 8 into 1 multiplexer. 8 is the number of input and 1 is the output, and these will be the select line on the basis of which one of the input will be the output. Let's see the next prerequisite, that is decoder. So what is decoder? Decoder is a combinational circuit that has n input lines and 2 to the power n data outputs, out of which only one output is activated based on n inputs. There will be n inputs and the count of output will be 2 to the power n. And if you see in decoder, only one of the output is activated among these n inputs. Okay, so let's see the examples. The examples are 2 into 4 decoder, 3 into 8 decoder and 4 into 16 decoder. So here it is the block diagram of 2 into 4 decoder. Why 2 into 4? Because the number of input is 2 and the number of output is 4. So it is 2 to 4 binary decoder. Let's see the truth table. So as there are 2 inputs, the possible binary combination is this, and you have read this that only one of the output is activated on the basis of n inputs. So in the output, if there are 4 outputs Q0, Q1, Q2, Q3, only one of the output will be activated. It means on 0, 0, Q0 is active. On 0, 1, Q1 is active. 1, 0, Q2 is active. And on 1, 1, Q3 is active. Now let's take the example of 3 into 8 decoder, as this one we will be using in our topic. So the number of inputs will be 3 and the number of output will be 8. 8 is power of 2 to the power 3. So 3 will be the number of inputs. Let's see the block diagram. These are the inputs and these are the outputs. So our next topic is general register organization. So first of all, we will study that why we are studying this topic. So the answer is that we are giving our inputs to the computer in the form of A, B, C, D, or if you're writing C program, you're giving some statements. You're giving it by using some syntax, and later on it is converted into an hardware language, that is assembly language. But our computer does not understand these words. Our computer understands only binary digits, that is 0 and 1. So we are going to study that how the commands given by us are read by the computer. So we will see a simple block diagram of general register organization of 7 registers. So we will see a bus organization for 7 CPU registers. So this is the block diagram for the bus organization for 7 CPU registers. Now we will see that there will be some registers, there are some mux, then there is an ALU, then there is a decoder. How these are helping us to execute any micro operation that we are going to study. Now first of all, we will see that there are 7 registers whose output are attached to a mux, that is multiplexer, and these 7 registers are attached to this as inputs. Now here you can see that there is one more input, and this is the 8th line. So 7 are the registers and 1 is the input line. Okay. Now see, let's have the example of R2 plus R3. The result of this will be stored in R1. This is the simple micro operation. We will see that how this micro operation is executed on this register organization in our CPU. So let's start. First step, mux A selector. Mux A selector. These are the select line for the mux A. On the basis of these select lines, the output of this mux is given. So mux A selector to place the content of R2 into the bus A. It means what will this select line? So whatever the input binary digits given to this, it will select one of the input of these registers or input, and that will be output. So in this micro operation, first input is R2. It means that R2 will come here. Next, mux B selector lines to place the content of R3 into bus B. It means now this mux has to give next input, that is R3, according to this micro operation. So R3 will be the output of this, and this R3 will be output of this on the basis of the select line B. So you have to remember that these are 3, these are 3. Okay. Now next step is ALU operation selector to provide the arithmetic addition. Now the operation that has to be executed is addition, and that can be done with the help of ALU. So next what will happen? R2 plus R3. So this will be done with the help of ALU. So the operation will occur and the result has to be stored on some register. How this will happen? because its output is connected to all 7 registers, but it is not possible to store this to all registers. It has to be stored on only one register. So how will be it decided that on which register it has to be stored? Decoder destination selector to transfer the content of output bus into R1. It means on the basis of this decoder, the result of this ALU operation is decided that on what register it will be stored. Okay, so it means now decoder is helping in placing the content to R1, which is the result of R2 plus R3. So this is the simple general register organization, and this is how a micro operation occurs in this general register organization. Now the point is that we have given or shown the micro operation on this general register organization, but computer does not understand the micro operation. It does understands the binary forms only. So let's see that how we can give that control word. What is control word? Control word is the sequence of binary digits. So what control word will be given to a system that it will understand that what micro operation it has to perform? First of all, we will see that there will be 14 binary digits which will act as control word that will be given to this general register organization, and on the basis of these 14 digits, this register organization will understand the micro operation. So let's see how. So we are having select A, that is for mux A. We are having select B, that is for mux B. We are having select D, that is for decoder. And then we are having OPR, operation in ALU. So as you can see, select A are 3 bits. See here, these are 3 bits. Select B are 3 bits. Select D are 3 bits, and OPR are 5 bits. It means it is 3 plus 3 plus 3 plus 5 count of digits, that is 14 binary digits, which can make this general register organization understand that what micro operation will be occurred. Let's take one example. Our example is that subtraction of R2, R3 will be stored on R1. So R2 will be selected with the help of select A. R3 will be selected with the help of select B. The result is stored on R1 and that will be decided with select D. And then operation subtraction, which will be decided on the basis of these 5 digits. So you have seen the fields, you have seen the symbol for this is R2, R3, R1 and sum. So what is the control word? Now I am telling that the control word for R2 is 010, for R3 it is 011, for R1 it is 001, and subtraction is this. So this whole will be the control word, which will be the input for this general register organization, and this is how a micro operation is understood and it will be performed on this general register organization. Now it means if we want to know that what is the input and what will be the control word, we have to see what is the encoding for these symbols. So let's learn the encoding for these registers and the operations. So first we will see the encoding of register selection field. This is the register organization. Now this is the table where you can see what will be the binary digits for each select line, and these will be the outputs. So if on select A 001 is the binary digits, then R1 is the output. Similarly for select B, similarly for select D. And if it is 000, it will be input for select A, input for select B, and none for select D, because input is only applied to mux A and mux B. So select D is not related here. Now this is the encoding for register. You know this already. How you know this? If you'll see these are all possible combination when there are three inputs. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And if you'll see, it is 0, 0, 1 having a decimal value of 1. So see, the outputs are R1. 0, 1, 0 is the binary form of decimal value 2. So see, the outputs are R2. 0, 1, 1 is the binary form of decimal value 3. So see, these all are R3. So you need not to remember this. This is something you already know. I'll take a note here that when select A or select B is 000, the corresponding multiplexer selects the external input data. That I have already told you. Now when select D is 000, no destination register is selected, but the content of the output bus are available on the external output. It means if it is 000, the output will be on external output. Okay. Now let's see the encoding for the ALU operation. There can be many ALU operations. There could be addition, there could be subtraction, there could be multiplication. Now we need to know that what are the encodings for these. Now here we are having some of the binary codes, then the operations, and then the symbol. Every operation is represented as symbol. So first operation is transfer A. The symbol is TSFA for transfer A, and the operation select. It means the binary word for this is 5 times 0 because it's a 5-bit number. Okay. For increment A, it is 4 times 0 and 1. For addition, it is 00010. For subtraction, it is 00101. For decrement, it is 00110. For AND operation, it is 01000. For OR operation, it is 01010. For XOR operation, it is 01100. For complement, 01110. For shift right A, it is 1 4 times 0. Then shift left A, 11100. Okay, and these are the symbols. This you must know if you want to write the control word in binary form for any operation. Now we will see some of the examples of micro operation. I'll show you some of the micro operations. These are some of the micro operations for which you have to write the symbolic designation. On select A, you need to write the first input register. On select B, you need to write the second input register. On select D, you need to write the output register, and operation you will write that what operation is in between for the register. Now pause the video and write all the symbolic designations for these, and then try to write the corresponding control word yourself. Hope you have done this. Now we will see here that what are select A, select B, select D and OPR. So in the first input register is R2. So R2 will be written over here. R3 is the second input register, that will be written over here. R1 is the output register, it will be written over here. And the operation is subtraction, that will be written over here. Now let's see the results. These are the symbolic designations for these micro operations: R2, R3, R1 and subtraction. For these fields, R4 first register, R5 second register input, these are written here, and R4 is the output register. It means the result of this will be stored on R4. What is the operation? OR is the operation. Here the first register is R6, second there is no register, but by looking at this micro operation, you can see that this is an increment A operation and the result is stored on R6. So here first register is R6, there is no second register, and the resultant will be stored on R6 and the operation is increment A. Here first input register, it is just a transfer of R1 to R7. So R1 is the first register, no second register, output will be on R7 and it is the transfer A. Here the first input register is R2, that is written over here, and the output is on some output. Okay, so there is no select D, it means there is no register over here, but it is the transfer operation that you know, so you wrote transfer A. Here the select A will be the input, there is no second register, there is no select D register, but this is the transfer operation. So you need to transfer from input to output. This is shift left operation. Whatever the content on R4 is, that has to be shift left. Then the resultant will be stored on R4. So R4 is the input register, there is no second register, and the resultant register will be on R4. Operation is shift left A. Now next we can see that we have to transfer 0 to R5. Now how this will happen? Now if you know that XOR operation gives 0 output when both the inputs are same. It means if 0 0 is there, output will be 0. If 1 1 is input, then output will be 0. So in XOR operation, if both the inputs are same binary digits, then the output will always be the 0. This is why here both the input select A and select B will give R5 as inputs and the output will be stored on R5, and if these both registers are XORed, then R5 will store 0 next. Next we will see the control words for these. Now see, these 3 bits are the select A bits which will give R2 as output. Now this is the binary form for the R2. This is the binary form for R3. This is the binary form for R1. And this is the operation code for subtraction. In this order, this control word is written. First we will write selection A, selection B, selection D, and then operation. Similarly, we can write the control word for each operation. See this one, R5, this is the code for R5. Similarly, for this B and D, R5 is the register. So 101 here, 101 here, 101 here, because all 3 registers are R5. And next, the operation binary code, that is 01100. Okay, so this is how, if we are having any micro operation, we can make the control word, and this control word is something on the basis of which that register organization gives the output. Next we will see the references. This content is given in Morris menu. You can also refer this book to understand these concepts. Thank you for watching the video. Hope you have learned something new.